Okay, so the last part of chapter 4 is about uniform circular motion. What are the forces on an object going in a circular motion? And specifically, we're going to focus on the case where this motion is uniform. So let's see what is uniform circular motion. So if we have an object going in, this thing used to have animations of animations now. If we have that, it's always changing direction. So its velocity is not constant. Even if we say uniform, the speed might be constant, but the velocity cannot be constant because it's changing direction. So that's the first point we have to think of. Now, if we look around us, there's a lot of examples of circular motion. For example, the Earth going around the Sun, the Moon going around the Earth. They are not perfectly circular, but they are close to circular. So for the first approximation, we can consider them as a circle. Now, if an object is going in a circle, I look at its position vector. So if this is the object, there used to be cars in here. Let me fix that for a second. Let's delete this. So if we look at the car going in a circular track, then and I choose the reference point as the center of the track, the position of the car is represented by this vector, the position vector. It's the position from the center to the location of the car at time t. The car is moving, so its position vector is changing. But what is constant is the magnitude of the position vector. The distance of the car from the center is constant. That's the condition for it to have a circular motion. Now, the velocity gives me the direction of motion. I'm moving on the track, so I'm moving parallel to the track. So the velocity is tangent to the track. So this is the velocity vector. It is tangent to the trajectory. So to stay on the circle, the position vector and the velocity vector has always to be perpendicular to each other. So that's the condition that I should have first. The first condition I should have to be on circular motion. The velocity at any time t has to be perpendicular to the position vector at any time t. Now, of course, for this lead us to have the magnitude of r to be constant. So r doesn't change magnitude, it only changes direction. Now, if the motion is uniform, circular, then also the magnitude of v has to be constant, and v is constant. If in this case, I can define the period of rotation, and the period is the time it takes to complete a full turn, and it is basically the perimeter of the circle over the speed. So the perimeter of the circle is 2 pi r over the speed v. That gives me the period t. Well, t comes from time. Capital T means the period. It's the time it takes to complete a full turn around the circle. So that's the condition to stay on a circle, is that v is perpendicular to r. Now, this is the velocity and the position. But if the velocity is changing, you see that the velocity, even though its magnitude is constant, the direction of the velocity is changing. The velocity here is pointing up, so this way. The velocity here is pointing down. So we have a change in velocity. So we should have an acceleration. So what acceleration, what is the acceleration required for us to stay on this circular motion? Again, our car disappeared. So if we have the car here, and the car does not have any acceleration, then it would move out straight. So any object that has zero acceleration, zero forces on it, zero net force يعني, it would move in a straight line with a constant speed. So the path, if we don't have any acceleration, goes straight out. So there should be something that is pulling us to the inside of the circle. So if I look at the car again here in this position, this is its velocity. If it doesn't have any acceleration, it should go up. So there should be an acceleration inward that is pointing inward that causes the change of the acceleration. If we look at the velocity also changes on a circle, and at any time it's perpendicular to the position vector. So the velocity vector also traces a circle. And to keep the magnitude of the velocity constant, the acceleration has to be perpendicular to the velocity. So the acceleration is on the radial direction. And we've seen from the direction, it has to be to the inside. We were using purple to draw the acceleration. So the acceleration has to be pointing this way at any time. So also the acceleration is not constant. The acceleration has different directions at different positions, but it is toward the center. So the centripetal acceleration, centripetal and toward the center. So to stay on track, there should be an acceleration that is toward the center of the circle. Now, what about the magnitude of this acceleration? If the acceleration is too strong to the inside, then this object is going to fall to the center. So it would start here, for example, and it will spiral in toward the center if the acceleration is too strong. If it is too weak, it would spiral out. So the acceleration has to be strong enough just to keep us on the circle. So if we look at how the velocity is changing, we take a small displacement. So we start here at R initial. We go here to R final. We move on this arc. The displacement is characterized by an angle d theta. Now, this angle is between R initial and R final. Now, V initial is perpendicular to R initial. V final is perpendicular to R final. So the angle between, if I draw V initial and V final from the same center, this is V initial, this is V final. The angle between them is the same as the angle between R initial and R final. My displacement, again, let's erase the ink. My displacement is from here to here. So this is delta R. Okay, now delta R, if we have a small angle, dr, the magnitude of dr, is given by r d theta. The same as here, I'm going dv. So dv, the displacement of dv, is v d theta. It's the same angle. Now, again, this is just a calculation without calculus. If I want to do it correctly, I have to use derivative and do calculus and change the coordinate system to polar coordinates, but just give us an idea how to find theta. So the acceleration is dv by dt. So with dv قلنا هي r d theta, but d theta by dt again is is dr or d theta. Here I can replace d theta from here. So d theta I can replace from it dr over r. So we have dr over r. So صار في عندي v over r. But dr over dt is what? Is v again. So I got v squared over r. The acceleration required for me to stay on the circle, or the centripetal acceleration required for the object to stay on the circle, is equal to v squared over r. It increases with how fast I'm going. The faster I'm going, the more the acceleration has to be. لأنه again, the acceleration, what the acceleration is doing is changing the direction. إذا أنا ماشي بسرعة 10 meter per second in this direction. then I have to, after a moment, I have to be moving with a speed of 10 meters per second in this direction. So I have to take the x component of the velocity to 0, and I have to take the y component from 0 to a certain value in this direction. So this requires a large acceleration, and the velocity is larger. If I'm moving with 10, than if I'm moving with 15, acceleration increases with the velocity. But it also decreases with the radius. The radius tell me how strong of a curve this circle is. The smaller the radius, the bigger the stronger the curve. بنسميها بالعربي كوع ضيق. اذا قعدنا بالسياره نحن عم نمشي على الكوع، اذا كان اضيق الكوع it means it has a smaller radius of curvature. So I have to change much quicker if I have a smaller radius. So the bigger radius means that I'm actually more straight. So it means I require a smaller acceleration. Actually, if I have a infinite radius, it means that I'm going on a straight line and I require no acceleration. So if A is equal to V squared over R, I will stay on the circle with a constant speed. If A is less than V squared over R, actually we would curve out and fly away from the center. If it is larger, it actually would fly in toward the center. So an object moving at a speed v in uniform circular circle with a radius r has a centripetal acceleration with a constant magnitude. AR equal to v squared over r. Now, if we have an acceleration, we require a force. So the net force on the object has also to be toward the center of the circle, and it should have a magnitude of mv squared over r. So this centripetal force is the net force on the object, not one of the forces that I would add to my system. So I have to look at what the forces that I know: normal reaction, tension, weight, friction, and see that they have to add up to a centripetal force that would keep me on track. So when we're drawing the force diagram, I don't include the centripetal force as an extra force, because that's not an extra force. That's actually the net force. I usually don't draw the net force. I draw the regular forces, and I look at their sum on it. Now, there is a common mistake that we have in physics, is that we think that if we are going in a circle, there's something that is pushing us out. There's nothing actually pushing us out. إذا مثلا واحد عم يلف الكوع بالسيارة بسرعة، تحسوا حالكم أنتم ضربتوا بالباب، ظهرتوا لبرا. هو in reality نحن ماشيين جالس. Our inertia, our mass resist change. It tries to keep going in a straight line. What's happening is the car is turning. If the friction force, or if we're turning very fast, if the friction force between us and the bank, or between our back and the bank, is not strong enough to keep us on track, بنزيح. Then we hit the door, بيرجع بصير في normal reaction من الدور, it would push us in. That's why we stay with the car. لو ما في باب, we actually نحن بنضلنا ماشيين جالس والسيارة هي اللي بتلف. So what to go, if there is no force, we go on a straight line. To go on a circle, we have to have a force, because a circle is not a straight path. So to stay on a circle, we always require a force that is pulling us to the inside of the circle. طيب. Before we start solving problems, I think I have something I can show you. Okay, so this site actually they have some nice animations of physics. So let's look at this, how the velocity and the acceleration and position vectors are changing when we go on a circle. So this is an object that going on a circle. We what they draw for us on the circle here, the blue line is the the pink line is the acceleration vector. The blue line it's x component, and the red line vector or arrow is its y component. And here on the graph they show us how the position, the x component and the y component changes with time. Actually, let's look at R first, the position. So this is the position vector. Let's stop it. So the purple line is the position vector. So let's go. So the position vector is pointing out from the center to the object. You see, it's actually one time it's here. When it's here, it's completely on the x-axis, then it's completely on the y-axis, then it's completely on the negative x-axis. So it's varying with time. So مرة بتزيد الx, مرة بتزيد الy. If you look at the box downstairs, you have r, the magnitude is x component and the y component are always varying. The change of position on the x-axis and the change in position on the y-axis. If you look at the velocity now, the velocity vector is tangent to the circle, but also the x component of the velocity is changing and the y component of the velocity is changing. Again, if you look at the box here the velocity is 15.7 meter per second. Vx is changing between minus 15.7 and plus 15.7, and Vy is changing between minus 15.7 and plus 15.7. The acceleration also is varying. Why we have so much short acceleration? Okay. So the acceleration, oops, too fast. So there is tower center, but it's also variable. Also a varying acceleration. So the force actually cannot be a constant force. It has to be changing in direction as the object moves. The force have to be also moving with it. So here they defining the period as 1.2 seconds. I don't know if we can change it. طبعا the frequency is just 1 over the period. Let me share this link with you on WhatsApp. Okay. Any questions so far? Let's move to solving some problems. I already have them solved, so I'm not going to delete them. Or should we delete them and solve them, write them manually? ما بعرف. Window. Oops. Okay, so uh, when you see this example thing, this is actually just a example in the book, so it's already solved in the book as well. So if you go to chapter 4, in the discussion of the lesson, they have some solved problems. So this is one of them. So a 0.525 meter string connects a 0.325 kilogram puck to a peg at the center of a frictionless air table. You know what is the air table? You've probably seen this air hockey game. بيكون فيها بخويش وبيطلع فيها هواء. This actually to just reduce friction. الديسك اللي بنلعب فيه على الاير تيبل we call it a puck. So the mass of this puck is 0.325 kilogram. مثل المسمار عندي puck and I'm connecting it with a wire to the center here. The tension in the string is 25 newtons, so they give me the tension. And the puck is actually rotating around, so it's going around in a circle. If we look at from the top view, I would see a circle going around. Find the puck's centripetal acceleration and its speed. So find the acceleration. I need to know the forces acting on the object. Now, if I look at it from the top, الويت والnormal reaction ما بيبينوا. الويت بيكون into the page والnormal reaction is out of the page. So I'm going to look at it from the side or from behind. So if I stand behind it here and I put my eye on the table and I look, I would see the weight. I would normal vertical up and call the y-axis. Now I will choose the vector or the axis that point toward the center. So this R is the axis or the direction that point toward the center. هذا الاكسس عم يمشي معي. So انا بس امشي بيبرم معي. So tension is always toward the center. So it is always on the R axis. So now I write Newton's law. I get W vector plus N vector plus T vector equal to MA vector. So when I project on the R axis, I got plus T equal to MAR. But AR, the acceleration, has to pointing toward the center. So this is the acceleration. So its R component is positive. So it is mv squared over R. So first here I can find the acceleration. So I can find AR is equal to T over M if I want to find the acceleration. If I want to find V, I can say that AR in magnitude is equal to V squared over R, capital R, the radius, والradius هو length of the string, so here is 0.525 meter. So I find that V is equal to RT over M. Okay? طيب. Another question. This is not from the book, but very similar. So a socket, a sock, يعني كلسات, stuck on the side of the closest dryer barrel بالنشافة على الزاوية تبع النشافة has a centripetal acceleration of 28 meter per second squared. If the dryer barrel has a radius of 27 centimeter, what is the tangential speed of the sock? So again, هيدا الكلسات هون عم يبرم بسيركل. The acceleration is radial. Well, velocity is tangential. So I want to find V. So for it to stay inside, the acceleration in magnitude has to be equal to V squared over R. So V is equal to the square root of A R times R. I have, of course, pay attention to the units. So if I want to get the speed in meter per second, I have to use everything in meter and seconds. The acceleration is given to me in meter per second squared. So I have to use the radius in meter. And I find the sorry, here I find the speed, but I also added to find the period. So it's 0.61 seconds. The period here, perimeter of the circle over the speed of rotation. Okay, another question which is not from the book, but it's also interesting. So a roller coaster car speeds down a hill past point A and then rolls up a hill past point B as shown below. So عندنا رولر كوستر هيدي السيارة بمدينة الملاهي بلشت هون نزلت على الاي وصلت على الاي طلعت ورجعت وصلت على البوينت بي هون. So this is point B. If the track exerts a normal force on the car 2.6 times 10 power 4 Newton at this point, what is the mass of the car? طيب هون لما كانت على البوينت A التراك تبع الرولر كوستر it's like a circle, an upward circle with a radius of 10 meters. هون على البوينت B when the track is like a downward circle with a radius of 15 meters. We know the normal reaction here at B. So they tell me at A. So we're still at A. So they tell me the normal reaction at A. Normal reaction على طول perpendicular to the surface out of the surface. So إذا أنا هيدا السيرفيس هون وأنا هون normal reaction بيكون طلوع. بس إذا أنا السيرفيس هون وأنا هون normal reaction كيف بيكون؟ إذا في normal reaction بيكون نزول. Okay? So at A the track is below me. So normal reaction is upward. هودي هن رسمينهم ولا أنا رسمهم؟ He confused me a little bit. اوكي هلا نوصل لبوينت بي نشوف كيف النورمال رياكشن اذا هيك ولا هيك. اوكي طيب نرجع للاي. طيب to stay on the circle I have to have an acceleration that is radial at any point. I have to have the acceleration that is radial that has a magnitude equal to v squared over r. انا بعرف السبيد at a. So بعرف السبيد وبعرف الراديوس يعني بعرف الاكسلريشن. So I want to find the mass of the car. So I apply Newton's law. So at point A عندي الweight vertical downward and the normal reaction vertical upward. I'm going on a vertical circle. So the radial direction is upward. The center of the circle is above me. So this is the center of the circle. So this is the radial direction. Okay. So I have W plus N equal to MA. I project on the radial direction. هلا فيكم سموه y direction بس you have to know that the acceleration is in that direction. I have minus mg plus n plus mar. The ar has to be positive because it has to be toward the center, and it's v squared over the radius of the circle. So the normal reaction is equal to mg ar. So قبل ما ننزل الm, let's look at this result. Normal at that point has to hold the mass لتبرمها. So الكار مش بس بدها تضل على التراك وتمشي جالس، بدها تمشي على التراك بس بدها تبرم طلوعها. So هون بدها تلف. So what is providing this turning force هو الnormal reaction. So that's why the normal reaction is mg plus mar. So I can find m, it's equal to 412 kilogram. طيب what is the maximum speed the car can have at point B for the gravitational force to hold it on track. إذا سرعنا كتير نحن جربينا امرار بالسيارة هيك بيكون في طلعة مثل مطبة إذا كنتم مسرعين كتير بتحسوا حالكم كأنكم عم بتطيروا بالهواء. What is happening basically is that the normal reaction below us is reduced, so we feel lighter. So the force that is pushing us down now is the weight. Now, for me to stay on track, I have to stay in contact with the track. So first I have to stay on the circle. I have to have an acceleration equal to v squared b over r. But the limit for it is that when n becomes 0, so zero normal reaction. So normal is not providing anything. So that's the limit. Of course, for me to stay on the track, n بدها تكون أكبر من 0. But on the limit, it can be 0. But I have to have an acceleration equal to v squared over r. هنا قايلين لي بدي gravitational force to hold me on track. So I have to have n equal to 0. So we still have the same idea, but now the radial direction that I want to choose is downward. Why? Because the center of curvature is below the object. So now mg is providing the centripetal force for me. So the n can be reduced. So I have mg plus 0 now equal to mar. So ar is equal to g. And this means that vb is equal to 12 meter per second squared. If I have a speed larger than 12 per meter squared, actually I would fly out of the trajectory. Make sense?
Doctor, بس please فيك تعيد at point B.
So at point B هن قايلين لي بدي الماكسيموم سبيد. نحن بنعرف انه كل ما تزيد السبيد كل ما required acceleration increases. Actually هي بدها تكون هيك مثل ما كنت رسمها قبل انا، هي فوق التراجكتوري. So البي هي هون. اوبس زعلنا الدنيا. So هيدي البي. اوكي. So لما تزيد الفيلوسيتي بتزيد الاكسلريشن. طيب limit that I could have on the acceleration هي انه ما عاد في normal reaction. اذا normal reaction upward وانا بدي الاكسلريشن downward, the maximum acceleration I could have هي when there is no normal reaction, when the acceleration only comes from the weight. So mg equal to mar if n is upward. Then I have ar equal to g. I cannot have an acceleration larger than that. ليه؟ لأنه there is no other force that is pushing me down. So the maximum acceleration downward I could have is the gravitational acceleration. So it means that I have a limit on how fast I can go on the track and stay on the track without flying off. So the maximum speed I could have here when the acceleration is equal to v squared b over r. So I need to stay on track. So I need my acceleration to be equal to the velocity squared over the radius. So vb is equal to the radius, square root of the radius times g. And rb is 15, g is 10, square root of, well, 9, approximately 12 meter per second.
Okay, thank you.
Right. Let's go back to the book. Another interesting problem that is not kind of straightforward at first هو the fact of how cars go on a curved road. So when a car goes on a curved road, the force that provide the turning force, the force that provide the centripetal acceleration that is directed toward the center of the curvature is actually static friction. Why? If we look at the top view of the car, this is the top view of the car. عم طلع انا عليها من فوق. هيدي الطريق الكيرفد رود. اذا في انجن فورس، الانجن بيكون عم يشدنا بهالطريقه. اذا في rolling friction بين الويلز والرود بيكونوا opposite to the direction of the velocity. على طول الكينيتيك friction وال rolling friction are opposite to motion. So I'm moving tangent to the trajectory. So this is the force of the engine. And this is kinetic friction, F kinetic. Now, إذا في weight بدها تكون into the road مثل كأنها فايتة جوات الصفحة من عندنا. والnormal reaction بدها تكون perpendicular to the road, so out of the page. Okay? يعني باتجاهنا. Now, for me to be on the curve, to curve with the road, إذا أنا ما في force عم تشدني لجوا, the car would actually move this way. يعني نكون نحن ماشيين مثل كأنه ما لفينا الكوع، الطريق لفت وأنا ضليتني ماشي جالس، ظهرت برات الطريق. There should be a force that is pushing me to the inside for me to stay on the road. هلا إذا بيجي بتطلع أنا بدولي بالسيارة، هن عم يمشوا parallel to the road. Perpendicular to the road, there is no motion perpendicular to the road. So if I will slide outside to the outside of the road. يعني أنا عم ببعد عن الطريق هون، لاحظتوا إذا أنا I would slide, I would move out of the road. ببعد عن الطريق. So for me to stay on the road, or because I might slide off the road, there would be a static friction into the road. So the static friction is what keeps me on the road. كرمال هيك لما الطريق تكون مي أو في ثلج أو في شيء منقط على الطريق, the friction, the static friction becomes very, very low, and that's why turning becomes very hard, because there's no friction to hold the car into the road. نفس الشيء أنا وقاعد مثلا على كرسي السيارة, what holds me from sliding out لما السيارة تبرم لجوا هو basically the static friction between me and the seat. Okay, so I have them written here. So the static friction is the force that is providing the inward force. But static friction have a limit. And the limit of static friction, Fs maximum, is equal to mu Sn. So eventually, no matter how good mu S is, if I'm moving too fast, I would actually slide out. So the maximum speed, the question is, what is the maximum speed when I'm turning with a radius of 20 meters? So this is the top view. Let's erase what we scratched here. If I look at the side view, a back view of the car, if I look from this side here, now this is the vertical axis, the y-axis. The radial axis هو هيدا radial axis. So this is my radial axis. I draw it here. Fs is on the radial axis. This is the normal reaction. And this is the weight. وطبعا في الفورسز بعد, the force of the engine والkinetic friction هن صاروا in the page, out of the page. Now when I write my Newton's law, I have W plus N plus Fs plus all these forces that I don't know about اللي هن parallel to motion, parallel to V or opposite to V, equal to ma. Now I want my acceleration to be radial. So I project on the radial axis, I have Fs equal to mv squared over r. So the friction force is what's providing the acceleration for me. Now, the maximum speed is at the maximum acceleration. So the maximum, friction. So the maximum friction I could have هي mu as n. So to find n, I project on the y-axis, the vertical axis. On the vertical axis, I could have no acceleration. I'm not going to fly off the road or go into the road. So mg is equal to n. So I can replace that back in this equation, and I can find that the maximum speed I could have is the square root of r mu s g. So it is proportional to the square root of r. كل ما كبرت الار كل ما في اسرع قد ما بدي. ليه؟ لانه قلنا الار هي قد ايه او عكس قد ايه كيرفد. سو كل ما كانت اكبر الار كل ما كانت ستريت اكثر الطريق. وكل ما كان في فريكشن اكثر كل ما كبرت الميو اس كمان في اسرع زياده. بس اذا كان الكيرف قويه والفريكشن قليله I cannot actually speed, otherwise I'm out of the road. So the trick in this question is to understand that rolling or kinetic friction are parallel to the motion. So if I'm moving in this direction, friction, kinetic, and rolling are in this direction. What the friction that is perpendicular to the direction of motion could only be static. And that's why they give us the coefficient of static friction. طيب. One way actually to get around this relying on friction to turn is what we call banking. So highways and racetracks curves are often banked. So the normal force provide a centripetal force and the car does not have to rely on friction. شو يعني؟ يعني إذا أنا هي التراجكتوري تبعيتي هي سيركولر بس اللي عم برسمها انتو ذا بورد بيكون جنب الطريق معلق. الطريق اللي عم بمشي عليها بتكون عالي من ميل برا واطي من ميل جوا. يعني الكيرف بحد ذاته الطريق بحد ذاتها مطعوجه. بعدني انا عم بمشي هوريزونتال بس عم بمشي هوريزونتال كيف هيك وماشي جنابي كيف واحد على البسكليت بيطعش حاله لما بده يلف او على الموتور. So that's basically what it is. بس الرود بتكون curved لانه الكارز cannot curve on their own. So this is our car. The car is still moving into the page. So the velocity is still into the page. But now because of the road is curved, normal reaction بطل vertical. Normal reaction صار عنده horizontal. Sorry. So normal reaction صار عنده horizontal component and a vertical component. So now what they tell us is that the Daytona International Speedway has one of the steepest bank curves of a maximum angle 31 degrees. So this 31 degree is the angle that the curve make with the horizontal. So this is the angle. On a curve of radius 320. So this is the radius of curvature of the curve. يعني احنا في عنا اللفه اللي هي لجوا اللي هي هيك عم نبرم هيك وفي عنا الانجل اللي هي sideways that I'm flipping the road with. So here we're working with 3 dimensions. What is the maximum speed for this curve assuming no friction? يعني بدي I want to find the force if there is no friction. هلا طبعا I could include friction but then the projections are going to be a little bit complicated لانه friction can only be parallel to the road. So static friction is going to be kind of this way. كمان رح تعمل angle مع الroad. I can include it but let's not do that for now. So n vector plus w vector plus the tangential forces equal to ma. I project on the radial direction. يعني انا باخذ الدايركشن radial تبعي toward the center وال y direction vertical. ما اخذت down the curve لانه I'm not going to slide down the curve. I want to go into the circle. So I want the radial direction because I know the radial acceleration. So when I project on the radial vector direction, I get mv squared over r plus mv squared over r. وهير الان now الانجل الان بيعملها مع الواي اكسس هي نفس ذات الانجل اللي بيعملها الكيرف مع الهوريزونتال. So this is the r component. So it is n sine theta equal to mv squared over r. But الان عندها شغله ثانيه. It has to still hold us from going into the road. So if I project on the y-axis, the acceleration is 0. So I got mg plus n cosine theta. And then I find n. So n is equal to mg cosine theta. I replace that back in here. And I can find v, it's equal to rg tangent theta. Now still it's very similar to that, but we replaced mu s by tangent theta. So now what is providing the centripetal acceleration for us is the how curved the road is, not how curved, how banked the road is. يعني قد ايه معليه من ميله واحده. So it's tangent theta. So rg tangent theta. Any questions? طيب I think it's a good place to stop here. ما أخذوا معنا كتير وقت لأنه already السوليوشن مكتوب السلايدز لو كنا نكتبهم نحن كانوا أخذوا معنا شي ساعة.